today's lecture, we are going to study what is meant by photoelectric effect. So, in this lecture, photoelectric effect means what? Then, what is the experimental arrangement of the photoelectric effect? Then, experimental results of photoelectric effect, which are also called as laws of photoelectric emission. Then, failure of classical physics to explain the photoelectric effect. Later on, Einstein's equation or Einstein's explanation of photoelectric effect. And finally, how Einstein's photoelectric equation by using quantum theory successfully explain photoelectric effect. All these points we have to study under this lecture. Now, what is meant by photoelectric effect? So, it was first discovered by the scientist Heinrich Hertz, who is a German physicist, and he discovered photoelectric effect in the year 1887. According to Hertz, whenever light of suitable frequency incident on a metal surface, then emission of electrons will take place, and this phenomenon is called as the photoelectric effect. So you can see here in this diagram, whenever light of suitable frequency incident on a metal surface. So you can see the metal surface which contains number of free electrons. Electrons are free means they can move freely inside the metal, but they cannot come outside the metal, because to come outside the metal these electrons requires certain amount of energy, which is called the work function, and that we have to discuss later on. So here you can see there are number of free electrons inside the metal, and now when this light incident on a metal surface, then emission of electrons will take place. You can see the electrons are emitted, and this phenomena is called as the photoelectric effect. Emitted electrons are called as the photoelectrons, and the current produced due to these electrons is called as the photocurrent. I have already mentioned that incident light should be of a particular frequency. Particular frequency means when a light of particular frequency incident, particular frequency or greater than that frequency, then only emission of electrons will take place. Below a certain frequency, emission of electrons is not possible, and that is called as the threshold frequency. So initially here it is shown that light of red color when incident on a metal whose wavelength is longer, means frequency is very less, then emission of electron does not take place. No electrons are emitted. But when a light of green color incident on a metal surface, then emission of electron take place, because for green color wavelength is quite smaller, and means frequency is more as compared to red, and that's why emission of electron is possible. If we again increase the frequency, you can see in third picture that light of blue color, when light of blue color incident on a metal surface, so for blue color again frequency is very high as compared to the green and red, and wavelength is small. So as frequency of blue color is high, that's why you can see emission of electron takes place, and electrons can move a longer distance. Longer distance means here it represents that they have a higher kinetic energy. So kinetic energy will be more. So this is about the photoelectric effect. What is photoelectric effect? When a light of suitable frequency incident on a metal surface, then emission of electrons will take place, and this phenomenon is called as the photoelectric effect, which was discovered by scientist Henry Church in 1887. Now let me discuss the experimental arrangement of the photoelectric effect. Experimental arrangement of photoelectric effect is as shown in figure. Here you can see this figure. This experimental arrangement consists of a evacuated glass tube. You can see this is a evacuated glass tube. So what may be the air or gas present in it? It is completely taken out and there is only vacuum, and that's why this tube is a evacuated glass tube having a small window. Provision of window is for incidence of light, so that the light radiation can enter inside the evacuated glass tube, and that's why there is a provision of a small window. Then it contains two electrodes. One is cathode and another is anode, and these two electrodes are connected to a battery. So here you can see the negative terminal of a battery is connected to cathode, while positive terminal is connected to the anode. Then there is a voltmeter to measure the potential difference or voltage across these two electrodes, and then there is a current meter, that is microammeter, is used to measure the photo current. Now here you can see when a light incident on a cathode is actually coated with a photosensitive material. Photosensitive material means which shows the photoelectric effect, and that's why when light incident on a cathode which is coated with photosensitive material, then that photosensitive material will emit the electrons. If frequency of the incident radiation is suitable, then as soon as that light incident on a metal, then emission of electrons will take place, and these emitted electrons will move towards the anode. As soon as they reach towards the anode, then the circuit will be completed, and here we get a photo current. So this is an experimental arrangement of photoelectric effect, and here it is observed that this photo current depends on the potential difference between anode and cathode. It depends on the intensity of light. It depends on the frequency. We have to study the effect of intensity here, effect of frequency, and then effect of the nature of the photosensitive material. Now let me discuss the effect of potential difference, effect of intensity, effect of frequency, and effect of nature of the photosensitive material on a photocurrent. So to study the effect of intensity on a photocurrent, we can study this effect from this graph. That second graph you can see here, which shows actually the effect of potential difference on a photocurrent. So frequency of the radiation will be kept constant, same photosensitive material will be used, and change the intensity. So you can see here we get two curves, that intensity is denoted as L1 and L2, and L2 is greater than L1. So intensity L2 is greater than L1. So here you can see as the intensity increases, then for intensity L1 photocurrent is less, while for intensity L2 photocurrent is high. Means here it is observed that as the intensity of incident light increases, then photocurrent also increases. So effect of intensity on photocurrent, it is shown in first diagram. which is the graph between intensity and photocurrent, and it is straight line. Means as the intensity goes on increasing, photocurrent also increases linearly. So this is an effect of intensity on a photocurrent, that is intensity is directly proportional to photocurrent. Second diagram shows the effect of potential difference on a photocurrent, and from this diagram you can see here x-axis, along x-axis we have taken potential difference. So after 0 it is positive, and towards left of the 0 it is negative, means polarity is reverse. And along y-axis we have taken photocurrent, and we have taken here two curves for again intensity for L1 and L2. So initially let me start from the potential 0. Here it is observed that when potential difference is 0, photocurrent is not equal to 0. It doesn't mean that it is not 0. Sometimes it may be 0 and sometimes it is not equal to 0. So photocurrent, when potential difference is 0, photocurrent is either 0 or may not be equal to 0. Here in this graph it is shown that photocurrent is not equal to 0. Now as the potential difference increases, initially photocurrent also increases. It goes on increasing. Then for further increasing potential difference, current becomes maximum. And after that, even though we increase the potential difference, photocurrent remains almost constant. That is called as the saturation current. So initially voltage is 0, photocurrent is either 0 or non-zero. In which increase in voltage or potential difference, current increases, initially increases and then becomes constant, that is the saturation current. Now if we reverse the polarity, means if we apply the negative voltage or reverse voltage, then here it is observed that here curves are not shown, but actually as the reverse voltage increases, then the photocurrent goes on decreasing. That photocurrent goes on decreasing, and at a particular reverse voltage, photocurrent becomes equal to 0, and that reverse voltage is called as the stopping potential. That reverse voltage is called as the stopping potential, and here you can see there is no effect of intensity on a stopping potential. Means stopping potential is independent of the intensity of the incident light. So this is effect of potential difference. Now we have to study the effect of frequency. What is the effect of frequency on a photocurrent? So from this curve here you can see it is observed that for positive voltages there is no effect of frequency, but when we apply the reverse voltage, then here we get three curves corresponding to frequencies nu1, nu2 and nu3, such that nu3 is greater than nu1, nu2 and nu2 is greater than nu1. So here you can see as the frequency increases, then stopping potential also increases. Means reverse voltage required to make photocurrent 0 also increases as the frequency increases. So stopping potential depends on frequency of the radiation. It is directly proportional to the frequency of the incident light, but photocurrent is independent of the frequency. There is no effect of frequency on photocurrent. Another factor is that the effect of frequency on a maximum kinetic energy. So, and in the same graph we can study the effect of nature of photosensitive material also. So to study the nature of effect of nature of photosensitive material, here let me plot the graph between maximum kinetic energy, which is taken along y-axis, and frequency taken along x-axis, and we get two curves for two different metals. And from this curve it is observed that as initially frequency increases, maximum kinetic energy is 0 up to certain frequency, and for further increase in frequency, maximum kinetic energy increases linearly. It goes on increasing linearly, and that frequency up to which maximum kinetic energy remains 0. The maximum frequency at which maximum kinetic energy is 0 is called as the threshold frequency, and it means below this frequency emission of photoelectrons is not possible. So the frequency below which emission of photoelectrons is not possible, that frequency is called as the threshold frequency. And here we can see in this diagram, for two different metals, threshold frequencies are different. Means to emit the electrons from the metal surface, different frequencies are required for the different materials. So this is the effect of photosensitive material on a maximum kinetic energy or the threshold frequency. Now we have to study the laws of photoelectric effect or photoelectric emission. So what may be the experimental results that we have discussed? So laws are nothing but the conclusions from these experimental results. So what are the conclusions? Photocurrent is directly proportional to intensity of a light. Here our observation is that photocurrent is directly proportional to the intensity of a light. Then photocurrent is independent of the frequency of the incident light. Photocurrent is independent of frequency, it does not depend on a frequency. Then stopping potential is independent of the intensity. There is no effect of intensity on a stopping potential. Then stopping potential is directly proportional to the frequency. Stopping potential is frequency dependent. It is directly proportional. Then there exists a certain minimum frequency below which emission of electrons is not possible. Means that frequency is called as a threshold frequency. So there exists a certain minimum frequency below which emission of electrons is not possible, and this frequency is called as the threshold frequency. So existence of threshold frequency. Again, maximum kinetic energy of electrons is directly proportional to the frequency. Maximum kinetic energy of the electron is directly proportional to the frequency. And photoelectric effect is an instantaneous process. Photoelectric effect is instantaneous process. Instantaneous process means there is no time lag between incidence of light and emission of electrons. As soon as the light incident on the metal surface, emission of electrons will take place. There is no time lag, and that's why photoelectric effect is an instantaneous process. And the definition of stopping potential, it should be kept in mind that the reverse voltage at which photocurrent becomes equal to 0 is called as the stopping potential. So definition of stopping potential and threshold frequency. are very important and that should be known to us. The minimum frequency below which emission of electrons is not possible, that is threshold frequency, and the reverse voltage at which photocurrent becomes equal to 0 is called as the stopping potential. Now we have to study the failure of classical physics to explain the photoelectric effect. In classical theory, photoelectric effect was explained on the basis of wave theory, but this theory fails to explain the following experimental results. So these are the experimental results which were not explained by the classical theory, and that's why classical theory fails to explain the photoelectric effect. So here you can see first one, according to this theory, as intensity of light increases, electron should emit with an increasing maximum kinetic energy. As the intensity increases, because according to classical physics, energy of the light should depend on intensity of a light. That's why as the intensity increases, then maximum kinetic energy should go on increasing. But in actual practice, there is no effect of intensity on maximum kinetic energy. Actually, maximum kinetic energy is independent of the intensity. Then this theory cannot explain frequency dependency of a photoelectric effect. We have seen that when the light of suitable frequency will incident on a metal, then only emission will take place. That's why, what is the role of frequency? Why photoelectric effect depends on a frequency? It cannot be explained by the classical theory. Then existence of threshold frequency, that is same point. The role of frequency in photoelectric effect cannot be explained by the classical theory. Then according to this theory, there should be a time lag between incidence of light and emission of electron from the metal surface. Because when light incident on a metal of suitable intensity, then what may be the energy required to free the electron? To get that energy, it should take some time. There should be some time lag between incidence of light and emission of electrons. But practically it is observed that photoelectric effect is an instantaneous process. As soon as light incidence on a metal surface, emission of photoelectron will take place. And these are the points which cannot be explained by the classical physics, and that's why classical physics fails to explain the photoelectric effect. Explanation of photoelectric effect was given by great physicist Albert Einstein by using Planck's quantum theory, and here Einstein derived equation which is also called as the Einstein's photoelectric equation. Now, photoelectric effect was explained by Einstein using Planck's quantum theory, and for this explanation of photoelectric effect, Albert Einstein was awarded with a Nobel Prize also in 1921. To explain this photoelectric effect, Einstein has made some assumptions. According to him, light consists of packets of energy or bundles of energy called as photons. That packet of energy or bundle of energy is called as the photon, and energy of that photon is h. Now, when light incident on a metal, then there is 1:1 interaction. 1:1 interaction means one photon will collide with one electron. One photon of light will collide with one electron of a metal surface. So 1:1 interaction is there, and energy of the photon what may be the energy of the photon when it collides with the electron? Then some part of the energy is given to the electron so that electron becomes free, and remaining part of the energy will act as a maximum kinetic energy of the electrons. So some part of the energy is utilized to free the electron from the metal surface, and that energy is called as the work function, which is denoted by W0, and remaining energy acts as a maximum kinetic energy. So from these assumptions, here we can write that energy of the incident photon, that is h nu, is equal to energy required to free the electron from the metal surface, that is work function W0, plus maximum kinetic energy. So maximum kinetic energy is half mv maximum square. Now apply the condition: if the energy of the incident radiation, that is energy of the photon, is just sufficient to free the electron from the metal surface. It is just sufficient to free the electron from the metal surface, so maximum kinetic energy will be 0, and that energy which is required to free electron from the metal surface is called as the threshold frequency. So condition is nu is equal to nu 0, then maximum kinetic energy will be equal to 0. So use this condition in above equation. So h nu 0 is equal to W0 plus 0, because maximum kinetic energy is 0, and therefore W0 work function is equal to h into nu 0. This is the formula for the work function, which we can use to solve the numericals also. That is W0 is equal to h is the Planck's constant, and nu 0 is the threshold frequency. Use this value of W0 in above equation. Then we get h nu is equal to h nu 0 plus half m v maximum square, and simplify, then half m v maximum square is equal to h nu minus h nu 0. If we take h common, then half m v maximum square is equal to h in bracket nu minus nu 0, and this equation is called as the Einstein's photoelectric equation. And by using this equation, that quantum mechanics successfully explain the photoelectric effect, and this is a success of quantum mechanics. Alright, so here one definition should be kept in mind, which is important one, that is work function. What is work function? Energy required to free electron from the metal surface. It is denoted by W0. Sometimes it is also denoted by phi 0. In some books it is denoted by phi 0 also, and its unit is, actually it is the energy, so it should be measured in joule, but that energy required is very small, and that's why generally its unit is in electron volt, or it is measured in electron volt. So this is Einstein's photoelectric equation. Now we have to see how the photoelectric effect can be successfully explained by using quantum theory. So here from this equation, Einstein's photoelectric equation, what we observe is that when h nu 0 is less than W0, h nu 0 is less than W0, or h nu is less than W0, that is the energy of incident photon is less than the work function of the metal, then photo emission does not take place. Thus there exists a certain frequency, that is nu 0, below which emission of electrons does not take place, and this is called as the threshold frequency. So from this equation what we have derived earlier, that is Einstein's photoelectric equation, we have seen that if the energy of the incident photon is less than the work function, then emission of electron is not possible, and that's why frequency dependence of photoelectric effect was successfully explained by the quantum mechanics. Again, according to this theory, intensity of light is proportional to the number of photons per unit time. Intensity means number of incident photons per unit time. So as the intensity increases, it means number of photons incident on a metal per unit time increases. As there is 1:1 interaction, because one photon interact with one electron, so number of electrons emitted are also increases, and that's why photocurrent also increases. So in this way, Einstein's photoelectric equation explains the relation that why photocurrent is directly proportional to the intensity. Then energy of photons depends on the frequency of a light, because energy of photon is h nu. So energy depends on the frequency. Hence, as frequency increases above the threshold frequency, then maximum kinetic energy of the electron also increases. But there is no effect of intensity of light on maximum kinetic energy. So the energy of photon, as it depends on the frequency, that's why as frequency goes on increasing, maximum kinetic energy also increases. But intensity increases means only the number of incident photons increases, not their energy, and that's why maximum kinetic energy is independent of the intensity. Then as energy of photon is not distributed over area, but it is in the form of a packets. It is in the form of a packets of energy, and so when photon is incident on an electron, all its energy is transferred to the electron without any time lag. As there is 1:1 interaction, as soon as that photon strikes or collide with the electron, then what may be the energy of the photon? That energy is instantaneously transferred to the electron, and electron becomes free. And that's why photoelectric effect is an instantaneous process. There is no time lag between incidence of photon and emission of electron. So in this way, what may be the failures of a classical physics in explaining the laws of photoelectric effect were overcome by the quantum mechanics, and quantum mechanics successfully explained all the laws of photoelectric equation. And lastly, we have to discuss what is meant by photon and properties of photon. So according to Einstein, light consists of bundles or packets of energy, and that bundle or packet of energy is called as the photon. Energy of this photon depends on the frequency of the light or a radiation. So energy is directly proportional to frequency, and according to him, energy of the photon E is equal to h nu, where h is the Planck's constant and nu is the frequency of the radiation or a light. Then second property is that rest mass of the photon is zero. Rest mass of photon is zero, means photon can never be at rest. It is always travels with a speed of light, and that's why it has a relativistic mass. According to theory of relativity, even though rest mass of photon is zero, but it has a relativistic mass, and that relativistic mass is given by, as we know, according to Einstein's mass energy relation, E is equal to mc square. Therefore, we can write m is equal to E upon c square. And as E is equal to h nu, so h nu upon c square. And simplify, then we get h upon c into lambda, because nu is nothing but c by lambda, and hence we can write here, since nu is equal to c by lambda, therefore we get m is equal to h upon c into lambda. So this is a relativistic mass of a photon, but rest mass of the photon is 0. Then momentum of photon, we can calculate the momentum, and it is in motion, therefore it has a momentum which is the product of mass, that is the relativistic mass, and the speed. So momentum of photon P is equal to m into c. Again m is h upon c lambda into c. So we get P is equal to h upon lambda. So this is a momentum of the photon. Then photon travels with a speed of light. The speed of the photons is equal to the speed of the light. Then photons are electrically neutral. Photons do not carry any charge, neither positive nor negative. Photons are electrically neutral. And as photons are electrically neutral, that's why there is no effect of electric or magnetic field on the photons. Means if the electric or magnetic field is applied to the photons, they will not be deflected. So these are the properties of a photon.